Okay, let's unpack this. What is the secret sauce that keeps the sun blazing day in and day out for billions of years?
Yeah, it's a fundamental question, isn't it?
It really is, and it's a question that, boggled minds throughout history. Even the sharpest scientific thinkers were stumped for quite a while.
Absolutely. What's truly remarkable is that the answers, or at least the journey to them, lie within the work of a scientific giant.
Right.
For this deep dive, we're delving into H.A. Bethe's Nobel lecture from 1967. Think of it as a first-hand account, really, of how humanity cracked the code of stellar energy production.
A scientific detective story, I like that.
Exactly.
And for you, our curious listener who loves to learn, consider this your streamlined guide to a monumental scientific achievement. We're cutting through the decades of research to bring you the core insights, how we move from some clever early ideas to the astonishing reality of nuclear fusion that powers not just our sun, but, well, the entire starry expanse.
So our mission today.
Our mission, to chart that intellectual adventure and really grasp the incredible engine of the stars.
Okay, so where did this quest begin? It started with a force we all know pretty well. Gravity.
Gravity, right?
Roughly a century before Bethe's groundbreaking lecture, Hermann von Helmholtz made a really bold attempt to explain the sun's energy just through gravitational contraction.
Right. The basic idea was, as those huge clouds of interstellar gas and dust collapse to form the sun, they gain gravitational potential energy.
Kind of like dropping something, right? It speeds up, releases energy on impact.
Exactly. Helmholtz figured the process itself was the sun's fuel. He even, crunched the numbers.
Yeah, he did. Using the sun's mass, which is just colossal, its enormous radius, and the universal constant of gravity, G.
That potential energy calculation, using the formula E equals GMMR, it pointed to a specific amount of energy released by every bit of the sun as it formed.
And from that calculation, they could estimate how long the sun could possibly keep shining at its current rate. Billman notes the radiated energy was measured at about 1.96 ergs per gram every single second.
So based purely on gravity, what was the verdict? What was the sun's lifespan?
Well, it came out to be, well, pretty short, actually, only about 30 million years.
30 million years. Okay, that sounds like a long time compared to, say, human history.
It does, initially.
But here's where a major problem popped up, right?
Yeah, a huge one. The timescale demanded by evolutionary biology, Darwin's work, the slow, gradual changes in life on Earth needed much more time.
Way more time.
Far, far beyond 30 million years. For their theories to hold water, the sun had to be vastly older.
So that immediately flagged a fundamental flaw in the whole gravity idea.
It really did. It was a significant conflict, and it highlights how interconnected different scientific fields are. You can't just look at physics in isolation.
Definitely not.
Then, right at the end of the 19th century, you get the discovery of radioactivity. Becquerel, the Curies.
Yes. That threw a real curveball, didn't it?
It did, because radioactivity gave scientists a new clock, a way to determine the age of rocks on Earth.
And those measurements pointed to?
Billions of years. A planet billions of years old.
Which meant the sun also had to be ancient. Billions of years old, too.
Exactly. Gravity just couldn't cut it. It couldn't provide energy for that kind of timescale. So the key takeaway here is that the first logical attempts, well, they fell short. Scientists needed something far more powerful.
Something hinted at incredible forces at play inside stars.
Precisely.
So gravity was out. The scientific community knew there had to be another, much more potent energy source. Enter Arthur Eddington in the 1920s.
Eddington. He really delved into the inner workings of stars, and he started playing with a truly revolutionary idea, something Einstein had paved the way for.
EMC saw.
EMC saw. Matter annihilation.
The idea that mass itself could be converted directly into energy.
And the sheer magnitude of energy that would unleash. I mean, Bethe points out that CNH, the speed of light squared, is just an absolutely enormous number.
So if stars could do that, convert mass directly to energy,
the sun's lifespan wouldn't just increase a bit, it would leap staggeringly to about 1,500 billion years.
1,500 billion. That's unbelievable. From millions of billions of billions?
It's a mind-boggling difference. Shows you the immense power locked within matter itself.
Talk about an incredible upgrade in fuel efficiency. But there was a pretty big snag, wasn't there?
A major one. No one had ever actually seen complete matter annihilation happen.
Right. Experiments showed protons and electrons didn't just, poof, vanish into energy. Not even over incredibly long timescales. Bethe mentions estimates of like 10, 30 years without annihilation.
Yeah, even Eddington himself recognized this was a huge hurdle. The observational evidence just wasn't there,
So annihilation was tempting, but didn't fit the facts.
which led to a crucial realization really taking hold in the early 1930s: nuclear reactions. Ah, okay. Not matter disappearing, but rearranging.
Exactly. The idea was that inside stars, under those extreme temperatures and pressures, the hearts of atoms, the nuclei, could actually interact. They could fuse together.
And release tremendous amounts of energy in the process.
Yes, it wasn't about matter vanishing, but about rearranging the protons and neutrons within the nucleus.
And the theoretical groundwork for this was already being laid.
It was. By giants like Gamow, Condon, and Gurney, they figured out how charged particles could sort of tunnel through the repulsive electrical barrier that normally keeps them apart. Quantum tunneling.
Quantum tunneling, right, like walking through a wall almost.
In a probabilistic sense, yeah. And then Atkinson and Houtermans and later von Weizsäcker started seriously exploring these thermonuclear reactions happening in the scorching stellar interiors.
So the pieces were starting to come together.
They were, and it all kind of crystallized at a pivotal conference in Washington, D.C. in April 1938, organized by Gamow.
What happened there? Well, astrophysicists gathered and shared their incredibly detailed models of what the insides of stars were like.
Okay.
And here's the amazing part. They developed these models without even knowing the precise energy source. They just assumed it was concentrated near the star's core.
Wow, so they knew the conditions, the temperature, the pressure, even before they knew exactly what was generating the heat.
Pretty much. It's incredible, isn't it? To do so much about something so far away, so intensely hot, just from observations and fundamental physics.
It really is amazing. Which brings us to the properties of stars themselves. I mean, you look up, you see all sorts of different stars, bright ones, faint ones, different colors.
And those visible properties tell us a remarkable story. Scientists realized gravity wasn't enough, nuclear reactions seemed promising. But how do you connect that to what we actually see?
Right. How do you test the theories?
That's where observing the stars, their brightness, their temperature, their color became crucial. It led to tools like the Hertzsprung-Russell diagram.
Ah, the HA diagram. A classic.
A cornerstone of astrophysics, as Beth mentions. It's basically a graph, right? Plotting a star's luminosity, its actual brightness, against its surface temperature.
And it reveals these distinct groups of stars.
Exactly. Most stars, including our sun, fall onto this band called the main sequence. It stretches from hot, bright blue stars down to cooler, fainter red ones,
And then you have others like red giants and white dwarfs.
which represent later stages in a star's life cycle. We'll probably get to those later.
Okay. And it turns out a star's mass is a real game changer in all this, isn't it?
Hugely important. There's a well-established relationship. The more massive a star, the vastly more luminous it is.
How much more luminous?
Bethe points out that just a 10-fold increase in mass can lead to something like a 3,000-fold increase in luminosity.
Whoa. 3,000 times brighter just for being 10 times heavier.
Roughly, yeah. It's a steep relationship. And this huge difference in energy output for more massive stars was another big clue. It suggested that maybe the sun's energy production mechanism wasn't the only one.
Right. Maybe hotter, more massive stars used a different, more powerful process.
Precisely. So, to understand the internal workings, astrophysicists rely on fundamental equations. Two key ones Bethe discusses.
Okay, brace ourselves.
Haha, maybe a little. First is hydrostatic equilibrium. That describes the balance between the outward pressure from the heat in the core and the inward pull of gravity.
The dPdR equation.
That's the one. dPdR equals SGMRERA. It looks complex, but it's basically just a tug of war. Pressure pushing out, gravity pulling in, keeping the star stable.
Got it. Pressure versus gravity? What's the other one?
The other key one is radiation transport. It governs how the energy generated in the core actually makes its way out towards the surface, mostly as radiation, as light.
So how the heat flows through the star.
Exactly. That equation, the one with 1d-2, again, looks intimidating.
That's it.
But the core idea is just describing how energy flows, how the temperature changes as you move out from the center. It involves things like opacity, how easily radiation gets through the stellar material.
So these equations describe a star in balance, with energy flowing outwards.
That's the essence. They also use the equation of state for the stellar gas, usually the ideal gas law, P equals ρ.
Pressure equals density times temperature, basically.
Pretty much, yeah. But with that extra factor, mu, the mean molecular weight,
What does that depend on?
it tells us the average mass of the particles in the star's plasma. Depends on its composition, how much hydrogen X, how much helium Y. and how much of everything else, the heavier elements, Z.
And for our sun, what are those numbers roughly?
Bethe gives typical values around XAN 0.65, Y as 0.33, and Z as 0.02 to 0.04.
So mostly hydrogen and helium with just a tiny sprinkle of heavier stuff.
Exactly, which is typical for stars of our sun's generation.
And using things like the virial theorem, which relates potential and kinetic energy, scientists could even estimate the temperature right at the center.
Yeah, Bethe mentions the formula KTC HMR, and it gives an estimate for the sun's central temperature,
Which is
around 15.7 million degrees Kelvin.
15.7 million degrees. Just wow.
It's at these truly mind-boggling temperatures and densities that thermonuclear fusion can actually happen. But there's still that big hurdle.
The Coulomb barrier.
Exactly. Positively charged atomic nuclei, like protons, naturally repel each other, like trying to push the north poles of two magnets together.
Right, they push each other away.
So they need a tremendous amount of energy, really high speeds, to get close enough for a different force, the strong nuclear force, to take over and bind them.
And the strong force only works at incredibly short distances.
Tiny distances, so they have to overcome that electrical repulsion first.
This is where quantum mechanics gets weirdly helpful, right, with tunneling.
Exactly, quantum tunneling. Even if the nuclei don't quite have enough energy to classically smash over that barrier,
They can sometimes just sneak through it.
there's a small but real probability they can essentially tunnel through it. It's one of the bizarre but true aspects of quantum physics.
And the chance of that happening is described by that reaction cross-section equation, SEE times an exponential factor.
That's the one, SEE. A key parts are SE, which sort of bundles the nuclear physics details, and that exponential term with EG, the gamma energy.
And the gamma energy tells you how strong that repulsive barrier is.
Basically, yes. Higher gamma energy means a tougher barrier to tunnel through. The crucial thing is that quantum mechanics allows this tunneling, making fusion possible, even when classical physics says it shouldn't be.
Okay, so tunneling gives them a chance. But what determines how often these reactions actually happen?
Well, several things. It depends on that tunneling probability, of course, but also on how many particles actually have energies close to the optimal tunneling energy. That's governed by the temperature, the Boltzmann distribution.
So how the speeds of particles are spread out.
Right. And pretty obviously, it depends on how many of the reacting nuclei are actually around their concentrations. The equation dx0 dt equals 7x0x1 just says the rate depends on the reaction probability and the amounts of the reactants, x0 and x1.
Makes sense. Like
Well-
needing enough fuel and enough sparks for a fire.
Good analogy. And Bethe highlights a really key point. It's not the average particles doing most of the fusing.
No.
No. The average thermal energy is actually too low. The reactions are dominated by particles way out in the high-energy tail of the distribution. They're rare, but they're the ones energetic enough to have a decent tunneling probability.
So it's the really fast ones that do the heavy lifting.
The most effective energy is around E0 equals 3 kT, which is significantly higher than the average kT.
And this leads to a very strong dependence on temperature.
Extremely strong. The rate goes up very sharply with temperature. That relation dl nev d dl nt33 shows that. Because itself depends on temperature, the overall dependence is very steep.
Which acts like a natural thermostat for the star, right? If it gets slightly hotter, fusion speeds up dramatically, causing it to expand and cool back down.
Exactly. It's a self-regulating mechanism. And it also means that the reactions involving particles with the lowest charge, hence the lowest Coulomb barrier, are the most likely.
Which means protons, hydrogen nuclei.
Precisely. Reactions involving protons have the smallest gamma energy, making them the most probable starting point for fusion in stars like the Sun.
Okay, so now we're getting to the actual recipes. The specific nuclear reactions powering main sequence stars like our Sun. You said proton reactions are key.
That's right. And the primary way this happens, the dominant process in stars like our Sun, is a sequence called the proton-proton chain, or PP chain for short.
The PP chain, what's the first step?
The very first, and actually the slowest step, is two protons, H plus H, fusing together.
But wait, two protons should just repel each other. How do they stick?
This is where another fundamental force comes in, the weak nuclear force. During that incredibly brief close encounter, one proton transforms into a neutron.
Ah.
So you end up with a nucleus containing one proton and one neutron that's deuterium, or heavy hydrogen. To make the transformation work, a positron, EU, an anti-electron, and a neutrino are emitted.
And this step is slow.
Very slow. Governed by the weak force, it's the bottleneck of the whole chain. Bethe gives the SE factor, a measure of the reaction probability, as tiny, 3.3610 UME barns.
So that slow first step sets the overall pace for the sun's energy production.
Absolutely. But once you have that deuterium nucleus,
Big speed up.
big time. Deuterium reacts very quickly with another proton, that plus H. This time it's a strong force interaction, much faster. It produces a nucleus of helium-3, He, 2 protons, 1 neutron, and releases energy as a high-energy photon, a gamma ray.
Okay, so proton plus proton makes deuterium. Deuterium plus proton makes helium-3. What happens to the helium-3?
Well, what happens next depends on the temperature inside the core.
Ah, okay. Different paths.
Exactly. Below about 15 million degrees Kelvin, which scientists often write as T6 EV 15, where T6 is temperature in millions of Kelvin.
Right, like the sun's core.
In those conditions, the most common thing is for 2 helium-3 nuclei to collide and fuse. He plus He.
What does that make?
It forms a stable helium-4 nucleus,
Hmm?
He, 2 protons, 2 neutrons, the common form of helium, and kicks out 2 protons, 2H.
And those 2 protons can go back and start the chain again.
Exactly. It recycles the fuel. And interestingly, this He plus He reaction has a surprisingly high probability, a large SE factor of about 5 MeV barns, according to Bethe.
So that's the main route in the sun.
That's the dominant branch, yes. But at slightly higher temperatures, another pathway opens up.
What's that?
A helium-3 nucleus can fuse with an already existing helium-4 nucleus, He plus He.
Okay.
This forms a nucleus of beryllium-7 and releases another gamma ray.
Beryllium-7. Is that stable?
It's radioactive, so
Yeah.
it doesn't stick around forever. It also has a couple of possible fates.
More branches. This chain is getting complicated.
It has a few twists. One possibility is that the beryllium-7 captures an electron from the plasma, Ab plus E.
Okay.
That transforms it into lithium-7 and releases another one of those ghostly neutrinos.
Lithium-7. Then what?
Lithium-7 very readily snaps up a proton, Li plus H. That forms an unstable beryllium-8 nucleus, which almost instantaneously falls apart into 2 helium-4 nuclei, Li.
Wow. Okay, so that path also ends up making helium-4.
It does. Alternatively, at even higher temperatures, the beryllium-7 might directly capture a proton, Eb plus H, before it has a chance to capture an electron.
And that makes...
That makes boron-8 plus a gamma ray. Boron-8 is also unstable. It quickly decays, emitting a positron and a neutrino, turning into that same unstable beryllium-8, which then splits into 2 helium-4s.
So it seems like all roads lead to helium-4 eventually.
In the PP chain, yes. Whether it's the main branch, He plus OHEL, or these side branches involving beryllium and lithium or boron, the net result is the same. 4 protons effectively combine to form 1 helium-4 nucleus.
And in that process, some mass is converted into energy according to E. Sukar.
Exactly. The mass of 1 helium-4 nucleus is slightly less than the mass of 4 protons. That tiny mass difference is released as a significant amount of energy, the energy that makes the sun shine.
Okay, so that's the PP chain. Works great for the sun. But you mentioned earlier that more massive stars are way more luminous. The PP chain alone can't explain that, right?
That's precisely the issue. The PP chain's energy output increases with temperature, but relatively gently, roughly as temperature to the 4th power.
Not steep enough for the really massive stars.
Not nearly steep enough to explain their incredible brightness. That's where the other main hydrogen-burning process comes in. The carbon-nitrogen-oxygen cycle, or CNO cycle.
The CNO cycle. Okay,
Okay.
so this involves heavier elements.
In this cycle, carbon, nitrogen, and oxygen act as catalysts.
Catalysts, meaning they help the reaction happen but aren't used up.
Exactly. They participate in the reaction steps, but they get regenerated at the end. The net effect is still the same as the PP chain. 4 protons turn into 1 helium-4 nucleus, releasing energy.
But it happens via a different route, using C, N, and O as intermediaries.
Precisely. It's a cycle of reactions.
Okay, walk us through the steps. How does it start?
It typically starts with a carbon-12 nucleus, EIC, the most common kind, capturing a proton, or OC plus H.
Now that makes...
It forms nitrogen-13 and emits a gamma ray. Nitrogen-13 is unstable, though.
So it decays.
Right. It undergoes beta plus decay fairly quickly, IOC plus EON-TC, turning into carbon-13 and releasing a positron and a neutrino.
Okay, so now we have carbon-13.
Carbon-13 then captures another proton, OC plus H, making nitrogen-14 plus another gamma ray.
Nitrogen-14, that sounds familiar. It's the main component of our air.
It is. And in the CNO cycle, it's a key player. Nitrogen-14 captures yet another proton, EOM plus H, to form oxygen-15 and a gamma ray.
Oxygen-15.
Also unstable.
Also unstable. Beta plus decays. Oh, EM plus
Hydrogen, yep.
EM into nitrogen-15.
Almost there.
Almost. Finally, nitrogen-15 captures a fourth proton, OEM plus H. This is the step that closes the cycle.
What does it produce?
It produces a helium-4 nucleus, there's our main product, and regenerates the original carbon-12 nucleus, ETF.
Ah, so the carbon is back, ready to start the cycle again.
Exactly. Carbon acts purely as a catalyst, facilitating the conversion of 4 protons into helium.
Now, what's the crucial difference between this and the PP chain in terms of energy output?
The temperature dependence. Remember, the PP chain went roughly as T.
Yeah.
The CNO cycle is much more sensitive to temperature. The slowest step in the whole cycle, the bottleneck, is the nitrogen-14 capturing a proton, AM plus H.
That one determines the overall speed.
Yes, and its rate increases incredibly steeply with temperature something like TEO to TBO near solar temperatures.
Wow, T to the 20th power or higher. Yeah, so even a small increase in core temperature dramatically ramps up the energy production from the CNO cycle.
And that's why it dominates in more massive, hotter stars. Their cores are hotter, so the CNO cycle just takes off.
Precisely. It completely outpaces the PP chain once you get above a certain temperature.
And nailing down the actual rates of these reactions, that required experiments, right?
Absolutely crucial experimental work, but that gives a lot of credit to W.A. Fowler and his team at Caltech. They painstakingly measured the strengths, those SE factors, for these individual CNO reactions.
That must have been incredibly difficult.
Extremely challenging. You're trying to measure reaction probabilities, cross-sections at the very low energies relevant inside stars, maybe around 20 keV.
But lab experiments usually run at higher energies.
Much higher, hundreds of keV. So you have to do these careful measurements at the lowest possible energies you can reach, and then extrapolate downwards.
And worry about things like resonances.
Exactly. Resonances are specific energy levels in the nuclei that can cause a huge spike in the reaction rate. You have to identify those and account for them properly. Fowler's work was essential for getting reliable rates for the CNO cycle.
And Bethe includes a figure 4, that shows this really clearly, doesn't it?
It does. It plots the energy production rate, epsilon, versus temperature for both the PP chain and the CNO cycle.
And you can see the PP chain dominating at lower temperatures.
Right, like in our sun, where the average energy production is about 2 ergs per gram per second, fitting nicely on the PP curve.
And then the CNO curve shoots up much more steeply and crosses over.
Yeah, the crossover point happens around 13 million Kelvin. T6 equals 13. Above that temperature, the CNO cycle quickly becomes the main source of energy.
So different stars use different engines, depending on their mass and core temperature.
That's a great way to put it. And there's even a slight variation, the CNO bicycle, involving oxygen-16 reactions, that fine-tunes things a bit.
Does the CNO cycle change the composition of the star over time?
It does, because nitrogen-14 reacts the slowest over long timescales in CNO equilibrium. Most of the initial carbon and oxygen tend to get converted into nitrogen-14. It becomes the most abundant of the CNO elements in the core.
Do we see that enhanced nitrogen on the surface of stars?
Sometimes, but not always. It depends on how well the material from the deep interior mixes with the outer layers. Often, the surface layers don't fully reflect the equilibrium composition achieved in the core.
Okay, so stars spend most of their lives on the main sequence, fusing hydrogen into helium via either the PP chain or the CNO cycle. But that hydrogen fuel in the core won't last forever.
It's inevitably finite.
What happens when it runs out? Both mentions that for stars a bit brighter than the sun, this can happen within the current age of the universe.
Right. For stars around twice the sun's luminosity, hydrogen exhaustion in the core happens in less than 10 billion years. So what happens next?
The party's over in the core.
The hydrogen fusion party? Yes. Without that energy generation, the core can no longer support itself against gravity.
So it starts to contract.
It does. The core, now mostly helium, begins to contract and heat up due to the compression.
But what about the layers just outside the core?
Ah, good point. As the core contracts and heats, the shell of hydrogen just surrounding it gets hot and dense enough to ignite.
So hydrogen fusion starts up again, but in a shell around the helium core.
Exactly. Hydrogen shell burning begins.
And what does this do to the rest of the star?
This has dramatic consequences. The intense energy pouring out from this hydrogen-burning shell pushes the outer layers of the star outwards, way outwards.
The star swells up.
Dramatically. This is what leads to the red giant phase. The star becomes much larger and cooler at the surface, hence redder. Bethe credits numerical calculations by Schwarzschild and Ibn for confirming this expansion.
Why does it expand so much? Is it just the shell burning?
It's complex. It might be related to the change in composition, the mean molecular weight discontinuity between the helium core and the hydrogen envelope, or possibly difficulties in transporting all that energy from the shell outwards efficiently. But the result is significant expansion.
And Bethe shows some figures illustrating this for a 3 solar mass star, right? Figures 6 through 9.
Yes, they track the evolution. You see the central temperature shooting up as the core contracts.
But the radius balloons out, then maybe shrinks a bit.
Right, and the central density goes way, way up. Interestingly, the star's overall luminosity doesn't change drastically during this initial phase, but the energy source has shifted to that shell.
And the temperature in that hydrogen-burning shell stays pretty constant.
Relatively constant, yeah. It's the contracting core that's getting really hot.
How hot does the core get?
It keeps contracting and heating until it reaches truly extreme temperatures around 100 million degrees Kelvin.
100 million degrees. And at that point,
A new fuel source ignites in the core. Helium.
helium fusion. Okay, what's the first reaction?
Well, technically there can be reactions like He plus Iono, but the really significant one for energy production and element building is the triple alpha process.
Triple alpha. Does that mean 3 helium nuclei?
Exactly. 3 helium-4 nuclei, which are also called alpha particles, effectively collide and fuse to form a carbon-12 nucleus.
3 at once. That sounds unlikely.
It is unlikely classically, but it happens in a 2-step process, greatly helped by resonances. First, 2 alpha particles fuse briefly to form unstable beryllium-8 plus OEMe.
Which falls apart almost instantly.
Usually, yes. But if, during its incredibly short lifetime, it gets hit by another alpha particle, plus OD,
Then you can make carbon.
then you can make an excited state of carbon-12, an OPC, which then releases a gamma ray to become stable carbon-12, I'll give you C plus O.
And resonances help this.
Crucially, there happens to be an energy level in beryllium-8 very close to the energy of 2 alpha particles, and another resonance in carbon-12 very close to the combined energy of beryllium-8 and another alpha particle. Salpeter and Hoyle predicted these resonances were needed to make it work efficiently.
Wow. Cosmic coincidences enabling carbon production.
Pretty amazing, isn't it? This triple alpha process kicks in around 110 million degrees. T6 is 110.
So now the star has a helium-burning core, making carbon. Does it stop there?
Not necessarily. Once you have carbon-12, it can capture another alpha particle to make oxygen-16.
Carbon to oxygen.
And oxygen-16 can potentially capture another alpha to make neon-20, plus O sheet. But building even heavier elements generally requires even higher temperatures.
What happens when the helium runs out in the core?
History repeats itself, in a way. The carbon-oxygen core starts to contract and heat up, and helium fusion ignites in a shell around the core. You get nested shells of fusion.
Like an onion. Hydrogen-burning shell, helium-burning shell, contracting core.
Exactly like that. And the core gets even hotter and denser.
So how are the really heavy elements made? Beyond carbon, oxygen, neon.
Bethe touches on this briefly. At even higher temperatures, maybe around 1 billion degrees Kelvin, carbon nuclei themselves can start fusing, carbon burning. Yes, producing things like magnesium-24 and silicon-28, as theorized by Hoyle and colleagues. And then oxygen can fuse, yield plus IO. These processes build up elements closer to iron.
Are there other processes too?
Yes, more complex chains involving capturing gamma rays, knocking out alpha particles, photodisintegration, and then recapturing them. These processes can rearrange nuclei and build stable isotopes all the way up to iron-56.
Iron. That's often cited as an endpoint, right?
It is for fusion energy release. Fusing elements lighter than iron generally releases energy, but fusing elements heavier than iron actually requires energy input. Iron has the most tightly bound nucleus.
So fusion stops being an energy source at iron. How do we get elements heavier than iron then, like gold, lead, uranium?
That requires different conditions. At the truly extreme temperatures reached in the final stages of massive stars, or in supernovae, billions of degrees, even endothermic reactions, ones that absorb energy, can happen.
Like breaking nuclei apart.
Right. High-energy photons can blast nuclei apart, releasing alpha particles, protons, and especially neutrons.
Neutrons. They don't have charge, so they can sneak into nuclei easily.
Exactly. These neutrons can be captured by existing nuclei, including iron, building them up into heavier isotopes. If a nucleus becomes unstable due to too many neutrons, it can undergo beta minus decay. A neutron turns into a proton, increasing the element number. This is the basis of processes like the S process, slow neutron capture, and our process, rapid neutron capture, that build heavy elements.
And where do these extreme conditions happen?
Primarily in the final death throes of massive stars' supernova explosions.
Supernovae, the big fireworks.
The biggest. When a massive star's core collapses after exhausting its fuel, it triggers an unbelievable explosion. This not only creates many heavy elements through processes like the R process, but also blasts all these elements, hydrogen, helium, carbon, oxygen, iron, gold, everything out into interstellar space.
Like the Crab Nebula, the remnant Bethe mentions.
A classic example. That explosion dispersed the elements forged inside the star.
So that material then mixes with interstellar gas,
And becomes the raw material for the next generation of stars and planets.
which leads to that incredible idea
Yeah.
that our sun isn't a first-generation star.
Very likely not. Our sun and its planets, including Earth, contain significant amounts of these heavier elements forged in previous generations of stars that lived, died, and exploded.
And Fowler's work showed the Big Bang couldn't have made much beyond helium.
Right. The Big Bang produced primarily hydrogen and helium with tiny traces of lithium. Pretty much everything else was cooked up inside stars and scattered by supernovae.
So Bethe concludes with this really elegant analogy, doesn't he?
He does. Stars having life cycles, just like living things.
Birth, growth, internal changes, death.
Exactly. Born from gas clouds, growing through fusion, developing internally as fuels change, and finally dying, often returning their enriched material back to the cosmos to seed new stars. It's a grand cosmic cycle.
So to bring it all together then, our understanding of what powers the sun and stars, it's been this amazing journey. From gravity,
Which was a good first guess, but the timescale was wrong.
through ideas like matter annihilation,
Which had too much power and no evidence.
to the intricate reality of nuclear fusion deep inside stellar cores, the PP chain for stars like the sun, the CNO cycle for more massive stars.
And then the later stages, helium burning, carbon burning, building heavier elements, all driven by this interplay between nuclear physics and gravity.
It's not just one process. Different reactions dominate at different times, not only providing the energy, but actually forging the elements that make up everything. You, me, the planet.
It's quite a story. And what's truly remarkable, as Beth's lecture highlights, is how it all came together. Theory, nuclear physics experiments done right here on Earth, and careful astronomical observations of objects light years away.
A real triumph of science. And hopefully, for you listening, you've now got a really solid grasp of these fundamental processes, a direct route to understanding this, drawing from the insights of a Nobel laureate.
Absolutely. It's complex stuff, but the core ideas are graspable.
And as you gaze up at the stars tonight, maybe just take a moment and let this sink in. The very atoms in your body, the carbon, the oxygen, the iron,
We're almost certainly forged in the fiery heart of some long-dead star,
scattered across space in a supernova billions of years ago.
and eventually became part of the cloud that formed our solar system, our planet, and ultimately us.
We are quite literally made of stardust.
It's a profound thought, isn't it?
It really is. Makes you wonder what other secrets are out there. Perhaps for another deep dive exploring those stellar life cycles in more detail, or the sheer power of supernovae, or diving deeper into how all the elements got made.
Plenty more to explore in the cosmos.